After the intense algebra in our last video in this series, I thought we'd take things a little more chill today, but still look at something pretty cool, because you could have one graph, you could have another entirely separate graph, but what happens if you want to smash them together into one big mega graph? Well, today we're going to investigate the idea of whether you can combine multiple graphs using one single equation. But before we get started, I must give you the usual warning. Yes, everything in this series is always done just for fun. You don't need to know these things for A-level, but we're looking at it anyway because we're interested in maths. Right, with that disclaimer out the way, let's rewind back to the beginning of the story, because the idea for this video came when I was teaching something on a previous, now defunct syllabus. This part of that exam required students to look at a graph of the form y equals a function of x, and then to be able to work out and deduce what the graph of y squared equals that same function of x would look like. It was quite an interesting idea, and to be honest, I might make a video on this concept at some point too, but we'll put that aside and just point out that it led to what we're doing today, because one of the first graphs that students decided to look at when looking at graphs of this form was y squared equals x squared. And when you actually take a look at the graph, it looks like this. And it doesn't take people long to realize when looking at it that, wait a minute, isn't that just a graph of y equals x and the graph of y equals minus x just smashed together in one big graph? Well, the thing is, you would be right if you thought that. But why? How is this happening? Well, it's fairly clear when you start to do some algebra rearrangement with it. Of course, if you've got y squared equals x squared, you want the graph to be of the form y equals, and therefore you want to get rid of that squared situation happening there by simply square rooting both sides. But of course, as usual, you've got to remember to do the square root with a plus minus in front of it to ensure you're including all the solutions. And of course, if you do that, that is what leads you to y equals x and y equals negative x separately. And there we go, straight away, we've shown a way you can combine two separate graphs into one big equation. But the problem is, this is rather restrictive. This is, as an idea in its current form, something we can only apply to be able to combine two graphs that are reflections of each other in the x-axis. I.e., in general, we could have y equals f of x and y equals minus f of x, and those two graphs will combine to make the graph y squared equals f of x all squared. But this is so restrictive. What happens if I want to just be able to take any two graphs and combine them into one big mega equation? How am I going to do that? Well, the approach we use so far is not giving us any clues. Yet, if we try a different approach, it'll give us another way of looking at this problem to show how we can adapt it to do just that. Instead of just starting with y squared equals x squared and just jumping straight to square rooting both sides, instead what you could do is move all the algebra onto one side of the equation. And then once you've done that, if you're eagle-eyed, you'll spot that this is difference to two squares, and therefore what we have can be factorized. In this case, it could be factorized to y minus x times by y plus x equals 0, which of course, by considering each of the factors in turn set equal to 0, leads to y minus x equals 0, or y plus x equals 0, which, what do you know, leads once again to those two equations of y equals x and y equals minus x. The reason this is interesting though is this is an approach we can adapt for our own purposes. Because if you just have a couple of graphs that have first been rearranged to be made equal to 0, then those two things are individually providing factors for a much larger equation that's been set equal to 0. So therefore we can reverse engineer this process to be able to combine any two graphs in the world we want. If you have y equals f of x and y equals g of x, rearrange both those equations to make them equal to 0, and then those will provide individual factors of one big mega equation containing both of those equations at once. So let's put this idea into practice. We could have the graph of y equals x squared, and then separately the graph of y equals x to the power 4, And then if we want to combine both of those graphs into one super graph, well, all you've got to do is individually rearrange these two equations to make them equal to 0. And then these two things are now going to provide the factors for our big mega equation. We're going to have y minus x squared times by y minus x to the power 4 set equal to 0. You could even then multiply out the brackets to disguise what was really going on here to end up with one big mega looking equation of y squared minus x squared plus x to the power 4 lots of y plus x to the power 6 equals 0. And there you go. We've just represented this graph using just one equation. And the cool thing is we don't just have to stop there. You could combine any number of graphs that you wanted to using this same process. For instance, what happens if we wanted to combine the graphs of y equals minus x, y equals minus 1/3 x, and y equals minus 3x all into one graph, which by the way would look like this? Well, you've just got to once again rearrange all those equations to make them equal to 0. Admittedly, because that equation on the left does have that 1/3 in it, which doesn't make it particularly nice, we could then decide to rearrange it by timesing both sides of the equation by 3, which eliminates the fraction from it nicely. But then we can go ahead and just multiply all these individual factors together to end up with this mega equation. And then, once again, if you really wanted to, you could then multiply out the brackets by first multiplying a pair of them and then multiplying the third one across, and then you end up with this crazy looking thing, but it really is just a graph of y equals minus x, y equals minus 3x, and y equals minus 1/3 x all in one graph. And in fact, you know what? Go ahead, get some graphing software and type that in and see for yourself. It really does happen. Okay, so that's how we can represent multiple graphs using just one single equation. But what happens if you're trying to do this idea in reverse? What happens if you're given one of these mega equations and you want to find out what individual mini graphs that one big equation is representing? Well, it depends on what you're given. If you're just given a more chilled example such as this one, some of you might just be able to look at it and instantly be able to factorize it by inspection. For instance, this one you might have spotted if you're eagle-eyed is just y minus 2x multiplied by y minus 7x. But what happens if you weren't able to spot that, or what happens if we just have a much more difficult example where that's not so easy to do? Well, if you got just two equations being combined and they're both of the form just y equals a function of x, did you know that the quadratic formula still applies? Sure, okay, it looks a bit weird, but we still got that y squared, y to the power of 1 and constant term from the perspective of y, except of course it isn't a constant because the coefficients are actually in terms of x. You could say that we've got an a coefficient of 1, we've got a b coefficient of minus 9x, and we've got a c coefficient of 14x squared. We can take those three things and plug them into the quadratic formula and it'll still work. For instance, in this case, we'd end up with y equals minus b, which would be minus 9x, plus or minus the square root of our b squared, minus 4 times our a times by our c, all divided by 2 times our a coefficient. And this is what you'd end up with. It looks weird because we're not used to usually actually directly plugging algebra into the quadratic formula, but interestingly, all will work out absolutely fine. You just have to simplify the things inside the square root, and that will get us an 81x squared minus 56x squared. Of course, both of those things are x squared, so you can gather the like terms to get just simply the square root of 25x squared. And then, because of the way square roots work, we can just individually square root the 25 and individually square root the x squared to end up with 5x. And what do you know? That's then something that's very easy to calculate, because if we just add on the 5x as one of the situations, we're going to end up with it simplifying to 14x over 2, which is just y equals 7x, or 9x take away 5x, which is 4x, divided by 2 becomes y equals 2x. And there you go. That once again confirms that this original equation we were given is just the graphs of y equals 7x and y equals 2x, both combined into one equation. Nice. And just in case you're wondering if this trick with the quadratic formula only worked because we had such nice simple graphs, still, as long as you're following the structure of two graphs of the form y equals a function of x, you will still be able to use the quadratic formula to separate it out. For instance, if we have this slightly more difficult equation, yet, admittedly some of you might still be able to factorize this by looking at it and guessing, but the quadratic formula would tell us, of course, we've got again an a coefficient of 1, a b coefficient of minus 1 lots of 7x cubed minus 4x to the power of 5, and a c coefficient of minus 28x to the power of 8. And plugging those into the quadratic formula, you will end up with this scary looking thing. Of course, you're then going to want to simplify the algebra inside the square root, so squaring out the brackets, and also doing the minus 4 times by the minus 28x to the power of 8. Blimey, that's a mouthful to say. You'll end up with this thing. Of course, you would then simplify the algebra some more, but then you've got to somehow square root 49x to the power of 6 plus 56x to the power of 8 plus 16x to the power of 10. What? Well, again, if you're paying attention, you might realize there's going to be a trick that's going to help us do this actually quite easily. Because of course, this bit inside the square root looks very similar to this bit that we had previously. And of course, that part of what we had under the square root came from this part up here, the b squared part of the quadratic formula. But of course, it's worth noting that something has changed from that expression, because now we've got a plus in front of the 56x to the power of 8, whereas before we had a negative sign. But that negative sign occurred because, of course, we had a negative sign inside the original brackets, so that meant when we did the positive 7x cubed times by the negative 4x to the power of 5, that's what ended up with a negative expression from multiplying those two bits of algebra together. But then if we want to adapt this to what we have now, if you just change that minus to a plus inside the final algebra expression, then all you've got to do inside the brackets is, well, potentially turn that to a plus as well, because then everything's positive, so when you're multiplying all the things by all the other things, it's going to end up with all the terms being positive. So therefore, the thing inside the square root is just going to factorize to 7x cubed plus 4x to the power of 5, all squared. Which now means the square root is going to cancel out with that square root nicely. And then we can just do, as usual, one separate thing with the plus and one separate thing with the minus for the plus minus symbol. Simplifying those two bits of algebra down, you're going to get y equals 14x cubed over 2 and y equals minus 8x to the power of 5 over 2, which then of course leads to the final answers of y equals 7x cubed or y equals minus 4x to the power of 5. And there you go. That is what this more scary equation was secretly representing. Two separate graphs that are individually quite nice, but when combined in the structure we had above, makes them look quite scary, but also more interestingly, it's those two graphs just all in one. But after doing all that, you might feel like we're just opening the door to even more questions. The fact that we can use a quadratic formula with algebra in it to solve things seems a bit strange, but therefore, if that's an idea that interests you, you really should consider subscribing to my channel, liking the video, and leaving a comment to let me know that you like this idea and you want me to make a video on it, because if you do, I will. And I've got loads of other videos on this channel in the Can We Do That series that give us the chance to explore loads of really cool maths not directly covered in the A-level syllabus. So with all that said, do consider checking out some of my other videos on my channel. I've got a link to another video in the Can We Do That series. I've got a link to the video in my previous series where we're trying to prove everything in the A-levels, both for maths and further maths. See you in a future video. Goodbye.